This lecture is going to be about pressure from a conceptual and explanation standpoint, and we will also be discussing units of pressure and pressure calculations. Some of the key concepts in more detail. We'll do both conceptual and mathematical models of pressure. We'll be explaining how a barometer works. One of the ways to measure pressure is with a barometer. It's not the most sophisticated anymore. It's not used that often, especially the one that I'm going to explain to you, but it is one way to measure pressure. We'll also be looking at some of the basic pressure units and maybe where those came from. There are many, many pressure units, and so you'll need to know some of those basic ones. And then also, because there are so many pressure units, we often need to convert from one to another, given whatever function we have to do within the chemistry setting. Looking at pressure from a conceptual standpoint, pressure is dealing with gas particles hitting the walls of their container. So that's sort of a definition of pressure. However, it's sort of tough to maybe understand that because we can't see it. We can't see gas pressure happening necessarily. You can't see the particles working. And so to model that, imagine cowboys at a saloon. And so the first sort of piece of this is in some movies you see the big saloon brawls where everybody starts fighting and punching each other, and there's guys going through the windows against the walls. So what you want to imagine are the pressure is anytime one of those cowboys, as they're fighting, runs into the wall and then goes back and fights more. Every once in a while you'll see one fly out the window. That force of all the cowboys hitting the walls at the same time would be pressure. Now there's of course other action going on inside. Not all of the particles inside or all the cowboys are hitting the wall. Some are within the main area of the saloon. But the pressure that we observe are when those cowboys hit the walls. Now, take a water bottle, an empty water bottle, for example. You might not know, why doesn't that, say, explode? Or why doesn't it collapse under the pressure of the atmosphere? And the reason is there's gases on both sides of that water bottle. You have the air on the inside of, we're talking an empty water bottle here. So there's air on the inside and air on the outside. So back to the cowboys. If you imagine that saloon door, if a cowboy from a long day on the range is walking in and then another cowboy's on his way out, if they both hit the door at the same time and push, and assuming they're equal strength, the door shouldn't move, right? Because there's two forces equally pushing on the same side. So pressure is the way you deal with sort of like net pressure is you got to look at all the forces involved. In most cases, pressure is equal on both sides of a barrier, and so there's no movement. But every once in a while, pressure is stronger on one side. So if one of the cowboys did happen to be stronger, bigger, whatever, he would be able to, say, overpower and push through. And so that would be where pressure on one side would collapse. Now, looking at it mathematically, pressure as a mathematical definition is the force per unit of area, so F over A. And so how do you increase pressure? Really, there's two ways to do that. The first is to, have a bigger force. So if you get those particles moving, say, faster, or if you have more of them, that's going to make for a bigger pressure. Another way you could increase the relative pressure is if you decrease the area. So if you have the same amount of people pushing on a small space, the pressure is more likely to, be stronger or, say, topple something over or whatever. Again, same force over a smaller area is going to increase the pressure. And now we'll get into measuring pressure. It started, sort of the founder of this is a guy named Evangelista Torricelli. He invented the barometer in about 1644. He was actually a student of Galileo. Towards the end of Galileo's life, or towards the end of his scientific career, he began thinking about vacuum tubes and maybe a vacuum is, of course, a glass tube where there is no air in it. So there's a lack of any particles whatsoever. So Galileo was interested in these and suggested them to one of his younger colleagues, being Torricelli, and he went through and began to experiment with them. And this is what he came up with over time. This is probably not the exact one, but this is the idea. He invented the barometer. And so what you have with this barometer is, this is all of this gray matter here is mercury. Okay, and there's this column here, and so the mercury rises up the column. And so then what happens is air pressure pushes down, right? So this is the air, it pushes down and then forces more mercury up into the tube. Now what makes it able to go up is that there is no air in here. This is a vacuum, so that's where the vacuum tube comes in. There's no air particles, so there's no resistance against the mercury rising. So if the air pressure were to, say, increase, the atmospheric pressure pushed down harder, this column would go up higher. If the air pressure was lower, meaning this arrow wasn't quite so much, it would sink back down, and this would drop down as well. And so atmospheric pressure used to be measured by the height of mercury. One of the common measurements was in millimeters. So if you've ever heard of the unit millimeters of mercury, it's relating to the pressure. And it's kind of strange because millimeters is a unit of length, but to measure pressure, those sometimes get confusing. So millimeters of mercury, anyway, comes from this. So here's what Torricelli found. At sea level, on a pretty consistent basis, the average height of mercury was 760 millimeters. And so that is kind of our base pressure value. Sea level, atmospheric pressure, 760 millimeters of mercury. It does change as you go at, say, a higher elevation. Moving up in altitude, there's fewer particles up there, fewer atmospheric gas particles. Fewer particles is going to imply less pressure. So that number 760 would go down. But that's kind of our base. So here are some pressure units. We have one there, millimeters of mercury. So 760 millimeters of mercury measures sea level atmospheric pressure. There's another unit, number's the same, it's called 760 torr. That's kind of a tribute unit to Torricelli. A lot of times units are named after people who made significant contributions to the field. Kelvin, Celsius, etc. Those are named after people. And then because 760 is kind of a weird number, those were normed to be equal to 1 atmosphere. So 1 atmosphere of pressure is equivalent to 760 millimeters of mercury, and also equivalent to 760 torr. And if only that were so simple. There are more pressure units still. So we got these 3, and here's 2 more. A Pascal is another unit of pressure. Now there's 2 here. There's the Pascal and the kilopascal, named after, of course, Mr. Pascal. Now this number here, these are the significant figures, and it's times 10 to the 5th. Now that's a huge number. And so it is often written like this as 10 to the 2nd, which is a little bit more manageable number. This is scientific notation. You'll sometimes see it written as 101.325 kPa. So that is kPa, kilopascals. And the reason this one is bold is because it's the System International, or SI, base unit. So this is kind of the official unit of pressure. It would be nice if it was 1 atmosphere. 1 atmosphere is actually used most commonly in most of our calculations, but the sort of official SI unit is kPa. And then a final one that maybe is more familiar to you is PSI, pounds per square inch. Again, force per area, right? Pounds per inches squared, force per area. So that's 14.7 pounds per square inch is equivalent to all of those other ones. We see pounds per square inch on a lot of our inflated tires. And so because there's so many pressure units, we need to be able to convert between them. Now these are all equal to each other. So when we do dimensional analysis, we can set them up as one fraction on top of the other, because 1 over 1 equals, well, 1. So here's one sample problem. I'm going to show this one. If you feel comfortable to do it, I would recommend pausing the lecture and then solving it. but the answer will be showing up in just a moment here. So if I wanted to convert from 745 millimeters of mercury to atmospheres, and then also to torr, here's how I would set it up. Start with the unit or the number in the problem, set up your T-chart to do your conversion, cancel out 760 millimeters of mercury. On top goes what you're trying to convert to, which would be 1 atmosphere. With dimensional analysis, remember, multiply across the top, divide what's on the bottom, and you should get excuse me, 0.980 atmospheres. Converting the same pressure to torr, 745 millimeters of mercury, setting up the T-chart, cancel 760 millimeters of mercury, which is equivalent to 760 torr. It kind of seems like a worthless conversion, but it is one just to know that you can convert from one pressure unit to another, and just know that these numbers match up with the units. And so, of course, you would get 745 torr. Another example here with the same starting, converting to kilopascals or kPa. 745 millimeters of mercury. T-chart. Again, I would recommend, if you haven't already, pausing the video and then trying this one yourself, and just make sure that you can get to the right answer. Canceling out millimeters of mercury with 760, converting to kPa. There's your conversion, 1.01325 times 10 to the second, and that equals 99.3 kPa. So, to recap, pressure measures the interior force of a gas. How hard are those gas particles hitting up against the interior walls of their container? You can measure the pressure with a barometer, and we explained how that works. And then finally, there's all those different pressure units. There's several of them, and you need to be able to convert between any of them, so going from one to another. And that's it for pressure and pressure calculations.